Hello, this time looking at Kirchhoff's circuit laws, the other two of the three fundamental laws of circuit theory. And there are two of them, Kirchhoff's current law and Kirchhoff's voltage law. We'll start with Kirchhoff's current law. There's various ways to write Kirchhoff's current law. The formal mathematical way is this. The sum of all of the currents flowing into a node is zero. Now, if you state Kirchhoff's law in those terms, it's very important to add this word net into the statement. The net implies that we are also considering currents flowing out of the node, but just as before, a current flowing out of a node is equivalent to a negative current flowing into a node. Perhaps a less confusing way to state it is the total currents flowing into a node equals the total currents flowing out of that node. Or a more informal way to think about Kirchhoff's current law is wires don't leak. In terms of the hydraulic analogy, there is no water, no fluid being lost from the system. Think of that in terms of a pipe diagram, something like this. We've got a junction here between three pipes. If X litres per second are flowing in this pipe, and Y litres per second are flowing into this pipe, then, if the pipes are not leaking, there must be X litres plus Y litres per second flowing out of this pipe. We could write, therefore, that Z must be equal to X plus Y. The total amount of fluid flowing in is equal to the total amount of fluid flowing out in 1 second. And that's all that Kirchhoff's current law says. The only tricky thing about it is to keep the signs of the currents clear. That the currents flowing in equals the currents flowing out, or if you want to add them all up and get the sum of zero, you have the currents flowing in, you multiply the currents flowing out by -1, so currents flowing out are effectively minus currents flowing in, add all of them up, and that should be equal to zero. Personally, I find that a bit confusing. I find it much easier to think of total current in equals total current out. Okay, that's Kirchhoff's current law. What about Kirchhoff's voltage law? This is Kirchhoff's voltage law. It has a similar looking mathematical expression, but this time it's the voltage drops around a loop in the circuit. So, for example, supposing I had a circuit with a battery cell there, a resistor there, and a resistor there, and I call the voltage here VA, the voltage here VB, and the voltage here VC. Now, going around the closed loop in this direction, the voltage between here and here would be VA minus VB. That's the voltage going from here to here. The voltage from here to here would be VB minus VC. And the voltage from here to here would be VC minus VA. Voltage across from there to there. Kirchhoff's voltage law tells me that the sum of these three is always equal to zero, which you might consider to be obvious, really, because all I have to do is expand these brackets, and I end up with VA minus VB plus VB minus VC plus VC minus VA, which is, if I just rearrange the terms a bit, VA minus VA plus VB minus VB plus VC minus VC, which is clearly equal to zero. And that is pretty much all Kirchhoff's voltage law says. The voltage drops across components around a closed loop like this. If you add them all up, you must get 0. Other ways to think about Kirchhoff's voltage law. Voltage is a function of where you are, not how you got there. For example, supposing we had a circuit, well, we could use the same circuit as the example, something like this. And I'm trying to get from here to here. There's 2 ways I could get from there to there. I can go this way, or I can go this way. That would imply that the voltage across this cell plus the voltage across this resistor must equal the voltage across this resistor. Because it doesn't matter how you get from there to there, the total change in potential that you go through must be the same. So if this is V, what did I call it before? Let's be consistent. VBA, that's VB and that's VA, and this would be VCB, and this would be VCA. So I could write VBA plus VCB is equal to VCA. Yeah, we can see some examples of these. Here's an example showing Kirchhoff's current law. This is a current source. It's forcing 6 milliamps to flow down here. This is another current source flowing 8 milliamps from left to right along here. Well, Kirchhoff's current law applied to this node at the bottom here would mean that the total current flowing in, which is 6 milliamps plus 8 milliamps, must equal the total current flowing out, 14 milliamps. So the ammeter is reading 14 milliamps, 6 plus 8. That's it. Here's an example of Kirchhoff's voltage law. We have the same circuit that I've drawn previously, this time with some real numbers in it. And the voltage across this battery cell here, I can draw this little arrow that says going from here to here increases the potential by 4 volts. This is 4 volts above this point here. Going from here to here decreases the potential by 1 volt. This is 1 volt below this point here. The voltage here minus the voltage here is 1 volt. Going down this way, the voltage across this component is minus 3 volts. The voltage here minus the voltage here is minus 3 volts. And the sum of these voltages around this closed loop is 0. 4 minus 1 minus 3, 0. And Kirchhoff's voltage law says that that is what happens in circuits. The total of the voltages across and around a closed loop is always 0. You could think about this in terms of the conservation of energy as well. Consider a unit charge moving around this circuit. The definition of voltage comes from consideration of energy. It takes 1 joule to move 1 coulomb through a potential difference of 1 volt. So, if we've got 1 coulomb, a unit charge, moving around this circuit, then we have to do 3 joules of work to get that charge up through this battery. The battery has to do 3 joules of work, 3 joules of energy is being put into the circuit. Across this resistor here, with voltage drop of 2 volts across it, the charge is losing 2 joules of energy. And across this resistor here, where the potential drops by 1 volt, the charge is losing 1 joule of energy. So it arrives back down here with the same amount of energy that it had in the first place. Got 3 joules, lost 2 joules, lost 1 joule, back where we are. If that wasn't the case, if this voltage here plus this voltage here plus this voltage here was not 0, then the charge would end up back at this point in the circuit with a different amount of energy than it started with. So if you left the circuit running indefinitely, the charge would either gain more and more and more and more energy, or lose more and more and more and more and more and more energy, eventually having an infinite amount of energy, or losing an infinite amount of energy. This makes no sense, because fundamental principle of physics is that energy is conserved. So we have to have this situation in which the total potential difference around a closed loop is equal to 0. Otherwise, conservation of energy is broken. Or is it? More about that one later. Okay, that's all I wanted to say about this time. Next time, we're going to have a look at the bad news. The fact that none of these laws actually work perfectly in practice.